This video is about the properties of liquids and how we can use intermolecular forces from the last video to help us explain how those happen. So the two types of properties we're going to talk about are cohesive and adhesive forces. So the last video was about intermolecular forces, and these forces are important because they help explain some of these unique properties of liquids. Liquids are cool and special, and there's some things that liquids can do that solids and gases cannot do. And that's what we're going to talk about. So the first type of forces is called cohesive forces. And this is the type of intermolecular attraction. Remember, we're talking about attraction between different molecules. And this is a type of attraction between identical molecules, molecules of the same thing. So if you have a bucket of water, this is the attraction between water molecules and other water molecules in the bucket. So one example of a cohesive force that we'll look at is called viscosity. You might have heard this before. Viscosity is the resistance of a liquid to flowing. So if something flows very slowly, it has a high resistance, it has a high viscosity. And if it flows very quickly, it has a low viscosity. So what factors affect this? What makes it viscous or not viscous? Oh, we gotta spell the word right. There we go. So what factors affect this? The size and the shape of the molecule affect it. And it's also affected by temperature. So when we say size and shape, what we really mean is the intermolecular forces. Remember our discussion of dispersion forces and how they depend on the size and shape of the molecule. So if we were to compare two different liquids, water and honey, we can look at how their viscosity differs. So water has a very low molecular mass. It's a pretty small molecule, and we know that it flows well, flows quickly when you pour it. You have no problems pouring liquid water. And that means that this has low viscosity, low resistance to flow. On the other hand, honey has a very high molar mass. It's very large, heavy, sticky molecules that make that up. It flows very slowly. If you were to hold the honey container upside down, it might not even come out because it's flowing so slowly. So this substance has a high viscosity, a high resistance to flow. But what if we change the temperature? Would honey change its tune? Cold honey versus honey that you microwaved and scalded yourself with, which I have done before in the morning. So cold honey has a low temperature, it flows very slowly. Looks like I wrote quickly instead of slowly. It flows very slowly, and that means it has a high viscosity. It has a high resistance to flow when it's cold because it has a low amount of kinetic energy. And here, for the warm honey, we have a high temperature. It flows much more quickly when it's been microwaved. So it has a low viscosity, low resistance. To make sure you don't get high and low viscosity mixed up in your head, just remember our honey versus water example. Honey is the most viscous. Okay, the next cohesive force we're going to look at is surface tension. This is something you probably know about but don't know how to describe. Surface tension is the amount of energy required to increase the surface area of a liquid. You might have noticed by the fact that water droplets on the window of your car tend to form droplets which are spherical. but liquids like to keep their surface area as small as possible because it's the lowest energy situation. So let's say we have a beaker full of a liquid. Let's take our microscope and zoom in on what the molecular situation looks like on something that's here in the center, that's surrounded by things. So you've got some water molecule here, and it is happily surrounded by lots of other water molecules on all sides, and on and on and on. So these molecules that are within a liquid, in the center, they are surrounded by other identical molecules on all sides, which is what it likes. It's the lowest energy situation. So this is a favorable situation because you're in the center of the liquid, surrounded by identical molecules on all sides. Let's take our microscope and look at a different spot. Let's look at the surface of the liquid. If we were to zoom in at the surface, we would see our molecules of interest at the center would be surrounded on some of the sides by molecules, but it wouldn't be surrounded by anything else above it because it's at the top. And the molecules adjacent to it at the top are air molecules and not water. They're different. So the molecules that are at the surface of the liquid, they are only 50% surrounded by identical molecules. 50% of that volume is touching a water molecule, and the other 50% is touching air. And so this is an unfavorable situation. The water wants to be touching all other molecules of the same thing, so it has the maximum cohesive forces. So what would happen if I pushed down on that surface? If I pushed down on it with my thumb, or if I was trying to float a penny on the surface, if I was doing something to push down, I would be trying to put a hole in that water to create another space where a water molecule was next to air instead of next to more water. So pushing down on the surface of the solution would be an example of creating more surface area. And creating more surface area takes more energy because it's unfavorable. We have to put in energy to overcome this unfavorable situation. So it requires energy input to break the intermolecular forces, the cohesive forces that hold those water molecules together. So some molecules are better at this than others, but in general, creating more surface area is unfavorable interaction. So those are cohesive forces that hold molecules to other molecules like themselves. But let's talk about the opposite type of forces, which is adhesive forces. Adhesive forces, you may have already guessed, that is the attractive forces between different kinds of molecules. So molecules of one thing interacting with molecules of something else. Different molecules. So most of the time when we're talking about adhesive forces, we are talking about a liquid and a surface, like glass, or concrete, or your face. We are interested in how well liquids like to interact with a particular surface. So as an example, we'll look at wetting glass. Not wedding with a D, like getting married, but wetting, like what happens when you get water on something. So we're going to zoom in on a test tube, which is what this is supposed to be, of a couple of different liquids. So if we have a test tube of water and we fill it halfway, the surface isn't going to be a perfectly flat line, right? There's going to be a meniscus, and the meniscus is going to bend downward slightly. So the downward meniscus is going to be lowest in the center. And let's say we fill this one with a different kind of liquid. Mercury, our favorite unusual metallic liquid. If we filled that one to halfway full, we know that the meniscus would look different than it did for water. It would actually bend slightly upward. We have an upward bending meniscus, highest in the center. And so we can explain why these phenomena occur based on the competition between cohesive and adhesive forces. So the cohesive forces are attraction between identical molecules. So this is the forces between one water molecule and another. And we're comparing that to the strength of adhesive forces, which is between different molecules. In this case, the water and the surface of the glass. So in this case, we can see that the meniscus bends downward in the center and upward at the side. And that tells us that the adhesive forces between the water and the glass is more favorable than between water and other water molecules. And so we say that water wets glass, as in it prefers to touch the glass. Let's compare that to the situation with mercury over here. So our cohesive forces are going to be forces between mercury molecules, and our adhesive forces are going to be between the mercury and the glass. And we can guess, based on the fact that the shape of this meniscus suggests mercury is trying really, really hard not to touch the glass, that mercury would prefer to touch other molecules of itself than to touch those molecules of the glass. So we say that mercury does not wet glass. So these are a couple of the properties of liquids that make them especially cool. And what's important is that we can explain each of these properties using our knowledge and information about the intermolecular forces between molecules of a liquid. So the next video is going to be about vapor pressure and the different phase changes between solids, liquids, and gases.